Okay, so let's chit chat. On those first multiple choice questions, 1 through 9, none of them should be A. I'll tell you that.
Ooh, okay.
Nice.
Well, guess that answer.
Better revise that one. Now, let's talk about
There we go.
problem number 1, where you had to draw this chart. And this was this whole summary of what Galileo did, and it was in sharp contrast to the Aristotelian view. So you should have a line that looks like this, okay? And here's the whole idea, is that when you have 1 kilogram, that weighs 9.8 newtons. If you have 2 kilograms, that's 19.6, okay? So this is where this all fits together. When Aristotle said, if you have Hank and you have Gary the golf ball, Aristotle says, and Aristotle was he was a philosopher, so he didn't believe in experimentation. So he goes, if you just feel these things, this thing feels heavier. So if you drop it, since it feels heavier, it should fall faster. And literally, for like 2,000 years, nobody bothered to test it. Aristotle said it, he was famous, he was brilliant, he influenced science, religion, politics. And no one bothered it. And now, they had a lot of other things going on. You know, bubonic plague, invasions of militaries. I mean, it was not a good time to be alive. So Galileo says, and this started this whole revolution in science, he went to leaning tower piece, he dropped a small cannonball and a large cannonball, boom, hit at the same time. So then they had to explain, well, why was this counterintuitive to the Aristotelian view about falling objects? So this chart answers this question. It's like, okay, and this is what I want you to see, is that if you have more mass and you have Gary, that has more stuff. They didn't understand the relationship with inertia. So I drop Gary, I drop Hank. Is there more force acting on Hank? Absolutely. But Hank also has more stuff. So it's harder to get Hank to move because he has more stuff in him, okay? So what this chart says, and if you want to look at it, this is, if you want to look at this slope without simplifying it, that's 9.8 newtons per kilogram, okay? So on Earth, for every kilogram of mass, this is what this slope means. For every 1 kilogram of mass that you have, you add 9.8 newtons of force to it in terms of a gravitational force. So if you double the mass, you double the force. But in contrast to that, when you double the mass, you double the inertia, you double the stuff. It's harder to get it to move. So get out of your minds right now the thought that, oh, gravity is the same for everything. It's not. Absolutely not. Does it cause the same acceleration? Yes. But don't tell me the gravitational force is the same for everybody. Does gravity end up causing the same effect? Yes, but the gravitational force is not the same. So on number 2, all of your answers on number 2 should be between, wait for it, Gapshawn, 3 and 9. Every answer on number 2 should be between 3 and 9. Pay attention to the number of significant digits that I gave you in those answers.
I have a feeling it was not 1. Okay, yeah. Give me a sec.
I didn't have a single significant digit.
If I get a convenient number, I don't want to waste the lead on extra.
Oh, because God forbid, because it looks like I gave you crappy data. 3 kind of builds it on itself. So your answer to 3B should be a little bit less than 1.
3B.
3B. Now, let's talk about number 4. So here's kind of a similar setup, and this is what we're gonna use today, this is a hydrogen-filled balloon. So imagine this is your 0.5 kilogram mass. You set it on the scale, okay? So gravity is pulling down with a force of 4.9 newtons. The scale is pushing up with a force of 4.9 newtons. Now, you take a balloon, helium-filled balloon, hydrogen-filled balloon, whatever, and you hook that up, okay? So with this balloon, clearly, there is an upward force acting, get over here. Clearly, there is an upward force acting on the balloon, okay? Because when I let go of it, poof, it flies up. But here's the whole key to this. When I hook this up, there's a little bit of upward force created by the balloon. Not much, a little bit. But does everything still add up to equal to 0?
Yes.
Yes. So therefore, the system isn't accelerating. So when I hook up the balloon, did that impact the gravitational pull between that mass and the Earth? Does that thing still weigh 4.9 newtons? Absolutely. That hasn't changed, okay? But what's happened is that this is taking some of the load off of the scale, okay? So when you look at that diagram on 4D, you should have 3 vectors. I want to know what they are, numeric value of each, and here's how you can check that your diagram on 4D is right. Add together the 3 forces that you have acting on them. If those 3 forces add up to equal to 0, you have a fighting chance of being right. If those forces do not add up to 0, I promise you it's wrong, okay? So you should have some positive forces, perhaps with 1 negative force, add them up. Punch them into your calculator if you don't trust your mental math. See if those forces add up to 0. If they do, you have a chance of being right. If they don't, I promise you, you're wrong. Okay? Cool with that one. Now, let's talk about number 5, because if your answer to 5A is wrong, everything's going to be a train wreck. Your answer to 5A should be pretty close to your current age.
Wait, number
What?
what? Number
5A.
What, Capshawn?
Yeah, it's just.
What do you have for your answer for 5A?
It's close enough.
What do you have?
17.9.
Yeah, perfect.
Okay.
He's just younger.
Oh, I'm assuming that you're seniors. So, you're not. I'm not gonna make an exception for you, Capshawn.
We have 2 seniors in here. Wait, how did you get 65? 47 newtons.
Now, here's the, yes, okay, your answer to 5A should be around 18. How about that? Oh, can't help it, you're a
Oh, I originally had it
child
right.
prodigy. Okay, so here's the story. So you're pushing this thing along and you stop. Again, you have to understand the only reason it stops is because there's an external force. Friction wants to keep it moving. So you stop pushing it, boom, it comes to a rest. And the only reason it comes to a rest is because there's an external force of friction. So, on 5, C and D, both of those answers should start with a 3. Was that well, good with that one, Gepshon? Okay. Your answer to number 6 should be something times 10 to the 3rd.
Oh, I didn't even think about that. I did. I just did it in extra sig figs.
Well, I'm just saying, no matter how you write it, it should be something times 10 to the 3rd.
So it's
Cool.
okay
If it's 1,000, it's going to be 10 to the 3rd.
Yeah.
Yes, caught.
So it's between
Also,
1 and
screw
2,000.
What?
1 and 9,000.
Also, I don't know
It's
why. I feel like the camera's just
1,530
turned
newtons.
Ever so slightly.
Yeah, how do you put that?
How'd you get 31?
No, okay.
God.
How do you put that?
Jeez.
What did I screw?
1.5 times.
All right, let's talk about let's talk about some of these problems out of the book. So when you look at 49, this is what I'm looking for on 49. An elevator suspended by a single cable has just left the 10th floor and is speeding up as it descends towards the ground floor. Okay? So this is going to form the basis of what we're going to talk today. A lot of these are what I call elevator problems. They involve helicopters and elevators. Elevator problems. So when you get to 49, and I cannot emphasize this enough, but if you understand this concept, these become relatively simple. Every force problem you're going to have can only fall into one of two categories. It's either accelerating, and the forces don't add up to equal to zero, and you have what we call a net force, which is the basis of today's lecture, or you have constant velocity and all of the forces add up to equal to zero. That's it. Those are the only two ways any force problem can go down. And then if you are accelerating, your only two options are it's speeding up or it's slowing down. Okay? So literally, you have constant velocity, make all the forces add up to equal to zero. It's accelerating, you either make it speed up or slow down. Every force problem is going to fall into one of three categories. Speeding up, slowing down, constant velocity. Net force adds up to equal to zero or it doesn't. So, obviously, elevators that don't accelerate don't sell very well. Okay? It's like, what does your elevator do? It just sits there. Does it accelerate? No. That's a good investment. So, here's the story. You're standing here in the elevator, right? What are the forces acting on the gravity? If the elevator's just right there, nothing is happening. What's happening? What's happening to that elevator?
There's gravity.
Gravity is pulling it down, and you have the tension in the cable. Okay, so anytime you have a string, something like that, a chain, we're going to call that upward tension. Now, no matter what happens, are you going to alter the gravitational force acting on that elevator? Is that going to change? Assuming that the number of people in the elevator, you walk in, boom, there's a certain number of people. Once you have a certain number of people, you are not going to change Fg. That's a fixed value. Okay? So basically what you do is you manipulate the tension side of the cable. That's where it comes into play. So visualize this. Where's my rubber stop? How will we use this way. Okay, so this is like the elevator. Okay, here's the elevator, here's the tension of the cable. Gravity is pulling down, this upward tension is balancing this out. You're on the 10th floor. If you want this to, and it says clearly on 49, is this the 10th floor and is speeding up as it descends towards the ground floor. Okay, so as soon as you see it, the word speeding up, slowing down, otherwise known as acceleration, you know the forces have to be unbalanced. Okay, you remember this for today's lecture. You see something accelerating, the forces are not balanced. So here's the story. So as this begins to go, am I going to increase the tension in the string or decrease the tension in the string to make it accelerate downwards?
Decrease the tension.
Yeah, because I want the gravitational force to be bigger than the upward force. So here's all you have to have. So on this one, when you got 49, you've got tension and gravity. The tension is going to be a little bit less than the gravitational. Now, when you get to stop, okay, when you approach the ground floor and it begins to slow down, then what has to be bigger?
Tension.
The tension, because then you're going to have an upward force that's bigger than the downward force, that's going to make it slow down. Okay? So all an elevator does is that it manipulates the relationship between the tension and the gravitational force acting on the cable. So here's what I'm looking for. So you got this, that's the only two forces in town. Gravity, tension. That's it. Okay? Tension's going to be a little bit less. Now, which direction are your velocity vectors going to point? Down. So draw V1. When you draw V2, is that going to be bigger or smaller than V1? Bigger, because it's speeding up. So draw V2 just a little bit bigger than V1.
And
So
V-
what's the direction of your acceleration? It's
Down.
either in the same direction or the opposite direction.
Same direction.
Boom. There's your acceleration vector. That's all you have to have. Okay?
Yippee skippy.
That's all you have to have. Same thing is going to be true on 50. Rocket is launched straight up. So here's the rocket, okay? And you remember this today. You always have to pay off the gravity mafia. So you have the gravitational force acting down. Captain Sean, if I want to get this rocket off the ground, does the force from the engines have to be bigger or smaller than the gravitational force acting on the rocket?
Bigger.
Bigger, or otherwise it's not going to get anywhere, right? So my force from the rockets, you could call it force applied, whatever, is bigger than that downward force acting on it. So if that's
Rocket.
bigger, which direction is the rocket going to accelerate?
Up.
Upward. Which direction is your acceleration vector going to point? Upward. Which direction are your velocity vectors going to get bigger? Upward. There you go. Now, let's talk about question 64. Okay?
Oh, I know you literally said, make sure you do 64. Yes, or whenever we left, I super forgot to do 64.
You should have circled it like I did.
For all practical purposes, 64 did not exist.
Well, it does exist in my reality, and that's the reality that really matters at this point.
Yeah, I know.
So here's the story on 64, and this is this whole idea of inertia, okay? And Newton's first law of motion. So basically, it harkens back to this whole idea that Mother Nature is a lazy prima donna, okay? So the question on 64 and the question that I gave you, question number 3, are kind of two sides of the same inertia coin, right? So imagine here you are, let's talk about 64. So here you are sitting here in the car, right? Driving along. And yes, the rules, the laws of physics do apply to you. So you're sitting there, we'd like to understand what's happening. The bench has no friction, no seat back, and there's nothing for you to hold on to, which is kind of a crappy deal. So do not confuse inertia with a force. Okay, inertia is not a force. There's only one thing that determines the amount of inertia an object has, and that's the amount of mass. More stuff, the harder it is to get it to move, but once it's moving, it's harder to stop. Inertia is not a force. So on question number 64A, what are the only two forces acting on this person?
Gravity and normal force.
There's only two vertical forces. There is only two vertical forces. Gravity and
Normal force.
normal force. That's it. There is no horizontal forces acting on you on 64. Okay? Because it says, draw a picture and identify all the forces as the car travels in a straight line at a perfectly steady speed on level ground. Okay? You are not accelerating. You are sitting here. You're going along like this. There are only two forces, gravity and normal. Now, you hit the brakes. Still, what are the only two forces acting on you?
Gravity.
Gravity and normal. Now, the car stops, but what do?
Continue moving forward at the
You
same rate the car
continue
was
moving
going.
in a straight line because you have inertia.
You fly
There
to
you
the
go.
front of the car.
And that's why you wear a seatbelt.
Exactly.
Not sure how this car got approved.
Sketchy. They paid off Department of Transportation. Okay. Make sure out of the book on problem 16, let me kind of give you how I want that to play out. So, what will be the acceleration that the forces have, okay? Make sure, for the love of all things physics, that you just don't say, oh, it's going to increase or decrease, or it's going to change. I will flip out, okay? You specifically tell me how that force is going to change if it does. Is it going to double? Is it going to be half as much? Is it going to be a fourth as much? Okay? Or if you want to do smash mouth physics, you can just go through and do the calculations. Okay. On the multiple choice questions out of the book, 21 through 26, none of your answers should be B.
I'll take B.
Dang it!
So 21 through 26, none of your answers should
21
be
was C.
B.
Oh yeah, I changed my.
Okay, so if two additional forces.
All right.
Oh, twice their additional force. I missed that part. Whoops.
Any questions at all? Will?
Hold on. I'm trying to find where I did 16 at. Am I retarded? I might be. Wait. Uh-oh. You said 16 in the book?
Yeah.
That's the wrong page. Is it okay if I just put numbers down?
On which one?
16?
Yeah, that's fine.
Okay.
But I said, just don't say, oh, it increases or decreases.
Okay.
Worse yet, oh, it's different, or it
Yeah,
changes.
I did not say anything at all.
Thank God.
Only
Okay.
numbers.
Anything else? Once, twice?
That one little girl that like, was asking,
Huh?
that one little like 8-year-old girl that was supposed to be like super smart and asking about a wagon.
Oh yeah, that.
Yeah, that one. It was number 18.
18.
Yeah. What about it?
What do you
The
want us to
wagon?
tell her? Like,
Huh?
she's asking too many questions. Like, genuinely.
Moon's first law.
Yeah, is it Moon's first law?
Think of other options.
It's like,
I do think it's
She's
interesting how it asks us how we would respond, not what.
I spent 30 minutes.
We would
just
say,
trying to figure
right?
out what to tell her other than just, hey,
For what
look,
question?
I'm gonna push it in front of you.
Okay.
Yeah, that girl's getting
Moon's first law.
tied up, tossing the
What
wagon,
does that
kicks
mean,
down a
Moon's
hill.
first law, though? Like,
Behold gravity.
It's exerting an equal and opposite force on you when you are
oh,
thrown
it's
down
funny.
the hill.
Are you drawing a pony?
Oh, okay.
I thought it was a giraffe at first.
It doesn't help.
Why? Do you need to specify?
Someone turn that horse into glue fast.
Oh, don't judge yet.
He
Straight to the glue factory.
Okay, so this is relevant to question 18. It's called the Legend of Newton's Horse. Okay?
Wait, the Legend of Newton's Horse? That's an
Yes.
actual thing?
Yes. Oh, wait, no.
It is now.
It is, it isn't, it should be.
Oh.
So according to the story, Newton has just published his work, The Principia, lays out his 3 laws of motion. Newton needs to go to town for book signing, something like that, maybe just to get a cup of coffee. And he hooks up the horse to the wagon. He climbs up on the wagon and he goes, yeah, horse. So, much to Newton's surprise, the horse, who has read his works, the Principia, which was written in Latin, by the way, and the horse can read Latin and translate it back into English. And the horse says, whoa there, big fella, I just read your works. If I pull on this wagon, the wagon's just going to pull back on me with an equal and opposite force. Therefore, there's no point in me pulling this because I'm not going to go anywhere. Because according to your laws, not suggestions, laws, I pull on the wagon pulls back on me, therefore I can never pull the wagon, let's call the whole thing off, I'm going to go eat grass. Chill out. So, imagine Newton's surprise. So how would you argue with the horse? Beyond just saying, I'm going to send you to the glue factory.
Behold, gun, pull or die.
Oh, that's intelligent.
When in doubt, threaten violence.
Let me ask you
Use the
this.
carrot and the stick.
Is the wagon and the horse the only set of forces involved
No.
in this story?
No.
If the horse does go to pole, because if the horse is right, you all are stuck here. Because if the horse is right, at the end of the block, you go to push on the door, what's the door gonna do?
Push back.
Push back on you with an equal and opposite force, you will never open that door,
Dang it.
okay? You will never open the door. You will never lift your keys, you will never lift your water bottle.
Unstoppable force versus.
Yes, it's like, Will's going, okay? So here's the story. Does the horse push on the ground?
Yeah.
Yes. What does the ground do?
Push back.
Push back with a set of equal and
and
opposite forces.
Force.
For those of you that have seen football or played football, why do you wear cleats?
Extra
Friction,
grip.
generate friction.
Yeah. So when you push down on the ground, that increases the
Pointy
force
foot.
that the ground can push back on you. So the whole key to this, as long as this set of equal and opposite forces between like the floor or the ground and the horse, or between your shoes and the door, as long as that set of equal and opposite forces is bigger than the set of equal and opposite forces, it is true. You push on the door pushes back on you. Okay? It's true. But as long as, now if you are standing on a frictionless surface, let's say I put a magic frictionless surface right in front of that door. You push on the door, what's going to happen?
You go backwards.
You go backwards. Okay, you would not be able to open the door if that was a frictionless surface. Okay, you would not be able to open up that door. All right. Anything else? Are we good, Danny?
What was it? 7D.
On which one?
The green paper one.
The what?
Like,
7E.
yes.
Okay. Well, look at this balloon, right?
Yeah.
So if I put a paper clip on here, and let go of the balloon, it goes flying up.
Yeah.
Okay? I attach it to a 200-gram mass, nothing happens. What's the difference?
The mass exerts more force.
Well, basically, it's a
Yeah.
comparison of the upward force in the balloon relative to the downward force of gravity. So since the downward force of gravity is more than the upward force of the balloon, it doesn't go anywhere. It's just like me. If I hold this balloon, I don't have to worry about floating up in the air. Okay? Now, am I going to weigh a little bit less? Yeah, because this is providing a little bit of an upward force.
Okay.
Okay? All right, anything else? Once, twice sold, Preston.
No, I was just gonna say, for number 18, the horse wagon problem, I said like means first law and inertia. Did you take that?
No, absolutely not.
We need the second one.
Absolutely not. Absolutely, 100% not. Okay? That does not explain, no. You need to talk about forces. You need to talk about, no.
If I talk about uneven forces, is that?
I
That, as
mentioned
long as you say something about forces, you just can't say inertia, first law, no.
force friction between myself and the ground as opposed to the wagon and the ground.
I can live with that.
Good.
Is it
Yippee
first or
skippy.
second force?
So I said like,
Cap Sean, it's killing me.
don't worry about it.
Gapshon, finishing blow, go.
Peer pressure,
I said the friction like allows you to stay on the ground.
I can live with that.
Okay.
You just can't say inertia.
Hey, is inertia the first or second law? Okay. You're right.
Second is F equals ma.
Okay.
Here's how you remember it. Inertia is one word. That's the first law.
Okay.
The third law is three words, equal and opposite.
Okay.
That's how you remember the third law. The second law is just F equals ma.
Okay.
Because 2 is in.
Two halves of the equation.
Huh?
Two sides of the equation. I don't know.
that are.
No, because 2 is a number, and numbers are using formulas.
There you go.
Good.
So,
Good.
so is 1 and 3.
Yes.
Well, 2 is odd.
Really? What kind of math they teach you in May South?
3 is a prime number, so it can't be the third law.
Because prime numbers suck.
But 5 is, I always thought is kind of a truth. 5 is like an honorary even number.
Yeah.
It's like Y in the alphabet.
No.
No.
Y is a dumb letter.
Is there any reason that they're in the
Because
order
it's
that
both
they
a
are?
It's like S.
valuable
Plus.
and-
S is so
That's
useful.
just how we
but-
publish.
No,
it.
no, no,
Found
no.
them like that.
Okay.
In that order.
Anything else? Let's go try soap. Stop the upper camera.
Stop the camera.